Find the radius of convergence and interval of convergence for the series from n equals 0 to infinity of x to the n over n factorial, well, x is a real number. Hence, show that the limit as n approaches infinity of x to the n over n factorial equals 0 for any x. So we will start with part A. Again, we're looking for a radius of convergence and interval of convergence. We are going to use the ratio test. So that means we need to find the lim as n approaches infinity of the absolute value of a, n plus 1 over a to the n. Remember, wherever this is less than 1, the series will converge. So that is going to be the lim as n approaches infinity of the absolute value of, well, it's going to be x to the n plus 1 over n plus 1 factorial. That's the an plus 1 term, over, which is going to be x to the n over n factorial. And remember, it's the absolute value of all of that. So that can be rewritten, quite a lot of rewriting we can do. As limits as n approaches 0 of, well, x to the n plus 1, we're going to write that as x times x to the n. And then we're going to write the n plus 1 factorial as n plus 1 times n factorial. N plus 1 times n factorial, exactly the same thing. If we divide by a fraction, we multiply it by its reciprocal, so that's going to be n factorial over x to the n. And remember, it's the absolute value of all of that. Look to cancel. We can take the x to the n with the other x to the n, and the n factorial with the n factorial. So now, remember, it's the limit as n approaches infinity. So the x terms are not relevant. We can pull those out. So we can say, well, it's the absolute value of x times the lim as n approaches infinity of, well, if we just look what's left, all that's left is a 1 over n plus 1. So now, if you look at that limit, well, as n approaches infinity, well, n plus 1 will definitely approach infinity, and 1 over n plus 1 is going to approach 0. So now we have equals the absolute value of x times 0, which equals 0 for all real x. So according to the ratio test, this particular series will converge no matter what value of x we have. Okay, so actually the value of x doesn't make a difference. It usually does, but in this case it doesn't. This series will converge everywhere. So this tells us that the series from n equals 0 to infinity of x to the n over n factorial converges for all real x. So if it converges everywhere, then the radius of convergence must be infinite. Just before that, make sure you say why we know that converged. It was the ratio test. So radius of convergence is infinite. And the interval of convergence is all real numbers. Remember, the interval of convergence, the set of values of x for which the series converges. Is all real numbers. Okay, so for part B, hence show that the limit as n approaches infinity of x to the n over n factorial equals 0 for all real x. So we're just considering the limit as n approaches infinity of the sequence, ignoring the series. So hopefully you remember back. So if a series converges, then the terms in that series, or the terms in the sequence, the limit as n approaches infinity must approach 0, because if it didn't, if these terms weren't approaching 0 for a larger and larger n, then the series couldn't possibly converge. Remember, series converge because as term numbers get greater and greater, the terms are so small that they don't actually contribute to the sum. So as the series from n equals 0 to infinity of x to the n over n factorial converges for all real x, then we know that the lim as n approaches infinity of x to the n over n factorial, it must equal 0 for all real x.